For more than 160 million years, dinosaurs dominated life on Earth. That's longer than mammals have existed in any recognizable form. During that time, continents shifted, climates changed, and sea levels rose and fell. Yet through all of it, dinosaurs persisted. They weren't fragile. They were one of the most successful groups of animals in Earth's history. By the late Cretaceous period, dinosaurs occupied nearly every major ecological niche on land. Massive herbivores shaped entire landscapes. Apex predators regulated populations. Smaller species adapted to forests, plains, and coastal regions. This wasn't a dying ecosystem waiting to collapse. It was mature, complex, and stable by geological standards. Then, 66 million years ago, something changed abruptly. A roughly 10-kilometer-wide asteroid struck near what is now the Yucatan Peninsula. The impact formed the Chicxulub crater and released energy equivalent to billions of nuclear weapons. Within a relatively short geological window, approximately 75% of species went extinct. The standard explanation is straightforward. The asteroid impact triggered global wildfires, injected dust and aerosols into the atmosphere, blocked sunlight, collapsed food chains, and ultimately eliminated non-avian dinosaurs. Mammals survived largely because they were smaller, adaptable, and able to exploit underground or sheltered environments. But here's what makes this event fascinating. The asteroid didn't sterilize Earth. It didn't reset life entirely. It removed dominance. The largest land animals disappeared, yet many smaller organisms survived. Within a few million years, mammals diversified rapidly. Eventually, one lineage developed advanced cognition, and that lineage is us. So here's a question. If an advanced civilization somewhere in the universe wanted to test whether a planet like Earth could support complex life long-term, what would they actually need to know? They wouldn't just need water and atmosphere. They would need to know whether large, energy-demanding organisms could survive for millions of years. Dinosaurs did exactly that. They weren't small or fragile. Some species weighed more than modern elephants. They required vast ecosystems to sustain them, and yet they thrived for over 160 million years. From a purely biological perspective, that's not just survival, that's planetary-scale success. Now, to be clear, there is no scientific evidence that dinosaurs were placed here artificially. The fossil record shows clear evolutionary transitions from earlier reptilian ancestors. But if we step back for a moment and treat this as a thought experiment, dinosaurs functioned remarkably well as a stress test for Earth's biosphere. They proved that this planet could sustain massive animals, complex food chains, and long-term ecological stability. They survived volcanic eruptions, shifting continents, and dramatic climate variations. If you were evaluating Earth as a potential long-term habitat, dinosaurs demonstrated that the system worked. And then suddenly, they were gone. Not gradually declining over tens of millions of years, not slowly replaced through competition. A single external event removed them in what is, geologically speaking, an instant. The system was not destroyed, it was cleared. If this were an experiment, it wouldn't look dramatic from the inside. There wouldn't be spaceships hovering over Cretaceous forests. It would look exactly like natural history. Evolution unfolding over millions of years, species adapting, ecosystems stabilizing. The test wouldn't interfere constantly, it would observe. From that perspective, dinosaurs were not just dominant animals. They were proof of concept. They demonstrated that Earth's gravity, atmosphere, and energy flow could support massive, metabolically expensive organisms for extraordinary lengths of time. That's not trivial. Most planets wouldn't pass that test, but experiments have phases. In engineering, once a system has proven stability under stress, you change variables, you remove components, you introduce new conditions, you observe how the system responds. And in Earth's case, 66 million years ago, the variable that changed was dramatic. The asteroid impact did not eliminate all life. That's important. It removed the largest competitors and reshaped the hierarchy. Mammals, which had lived mostly in the ecological margins, suddenly had access to open niches. In evolutionary terms, the constraint was lifted. And here's the striking part. Mammals diversified rapidly after the extinction. Within a relatively short geological time frame, they expanded in size, behavior, and ecological range. Eventually, primates emerged. Then one primate lineage developed unusually large brains, relative to body size. Now, none of this requires alien intervention. Evolutionary biology explains the sequence well. But if you were designing a two-phase biological experiment, first test planetary stability with large reptiles, then test adaptive intelligence in mammals, the transition would look remarkably similar. The asteroid becomes the pivot point, not necessarily a weapon, not necessarily intentional, but a reset event. In complex systems, resets aren't always failures. Sometimes they're necessary to transition from one configuration to another. There is, however, a more grounded scientific angle that intersects with this idea. Organic molecules have been found in meteorites. Amino acids, the building blocks of proteins, can form in space. The early Earth may have received critical chemical ingredients from extraterrestrial sources. That doesn't mean humans arrived on an asteroid. It means that space and biology are not entirely separate domains. Chemistry moves between planets. Material is exchanged. Life, at least at the molecular level, may not be confined to one world. So now the question becomes more precise. Could external forces, whether natural or intentional, have shaped the trajectory of life here in ways we're only beginning to understand? Let's consider a second possibility. Suppose an advanced civilization somewhere in the universe faced extinction on its own world. Its star was destabilizing. Its resources were collapsing. If relocation were possible, Earth 66 million years ago would have looked promising. It had liquid water, a breathable atmosphere, and a stable orbit, but it was not empty. It was dominated by massive, territorial, well-adapted species. Coexistence would not be easy. Large megafauna shape entire ecosystems. They resist displacement. From a purely strategic standpoint, redirecting a 10-kilometer asteroid requires far less sustained effort than planetary invasion. Orbital mechanics can be influenced gradually. A small gravitational adjustment, applied early enough, compounds over time. We know this because we've already tested the principle. In 2022, NASA's DART mission deliberately altered the orbit of a small asteroid. The change was measurable, modest, but real. That's with our current technology, a species that only began launching rockets a few generations ago. Scale that capability forward by thousands or millions of years. An advanced civilization wouldn't need to build a weapon. They would use what already exists. Physics would do the rest. The event would appear natural to anyone studying it millions of years later. But here's the part that changes everything. Whether the asteroid was random, seeded, or redirected, the end result is the same. A dominant species was removed, the ecological hierarchy reset, and eventually another species rose to dominance. That species now tracks near-Earth objects. It simulates planetary impacts. It models extinction events. It has the capacity, not yet perfectly, but increasingly, to alter celestial trajectories. For the first time in Earth's history, a native species possesses the capability to do exactly what ended the dinosaurs. Not accidentally, intentionally. So perhaps the deeper question isn't whether we were seeded or whether aliens intervened. Perhaps the real question is this. When intelligence reaches a certain threshold, does planetary engineering become inevitable? The dinosaurs ruled for 160 million years and never saw the sky change. We have ruled for a fraction of that time. And we already know the sky can change. We already know how. At Terminal, we explore systems like this, not to predict fantasy, but to understand possibility. If you believe the future is something we build, not something we wait for, subscribe, turn on notifications, and join the conversation in the comments section below. Because the next breakthrough begins with better questions.